Welcome everyone to the Combinatorics Onwards seminar. Our speaker today is Colin Defant, who is just about to finish his PhD at Princeton University, and he's going to talk to us today about antipowers in aperiodic recurrent words.
All right, well, thanks for the introduction, and thanks everyone for coming. Thanks for the invitation to speak here. So I think I probably don't have a full 50 minutes worth of material. I realized this as I was practicing yesterday. So if anyone wants to, interrupt at any time and have some kind of discussion, that's totally fine. I'm not, trying to rush through the material or anything. So I guess I'll start with powers, which is probably familiar to most, if not all of you. But a k-power is just a word of the form w to the k for some non-empty word w. So it's just a word that you get by concatenating some word with itself k times. As an example, the word 110, 110, 110, 110 is a 4-power because you get it by concatenating 110 with itself 4 times. So another way that you can think about this is that a k-power is just a word that you can break up into k consecutive blocks that are all identical. And this motivated Ficci, Restivo, Silva, and Zamboni in 2016 to define sort of the opposite notion of a power, which is that of a k antipower. And this is a word that can be broken up into k blocks that are all of the same length, but they're all distinct. So an example of this would be if we take the word 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0. This is a 3 antipower because we can break it up into these 3 blocks that all have the same length. They all have length 4, but they're all distinct. Right? However, this word down here, 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, is not a 3 antipower because if we try to break it up into 3 blocks of the same length, then 2 of those blocks are the same, the first one and the last one. Okay, so these authors were kind of approaching this from a sort of Ramsey theoretic point of view, where they said, well, we have these 2 different types of structure. One is powers and one is antipowers. And we'd like to say that maybe it's impossible to avoid both of these types of structure. You have to contain at least one of them, if not both. And so the theorem they proved is that if you have any infinite word over any alphabet, then it has to contain either powers of all orders, and by that I mean k powers for all values of k, or it has to contain antipowers of all orders, meaning k antipowers for all values of k, or it could have both. Now there's also a finite version of this, which says that you can define in of lk to be the smallest positive integer, such that every word of length in of l comma k contains either an L power or a k antipower. And so this is some kind of analog of like the Ramsey numbers. And so we might be interested in trying to find estimates for these numbers. It seems probably very difficult to compute these numbers exactly for large values of L and K. You can probably do it for small values of L and K. And I think they worked out some of them in the paper. But really, it's maybe more tractable to look for estimates. And one of the things they did is they looked at these sort of diagonal Ramsey numbers, this in of k comma k. And they show that it's somewhere between k squared minus 1 and k cubed times k choose 2. So it's somewhere between quadratic and quintic. So I think it would be interesting to sort of narrow these bounds and try to say, is it how fast is it growing? At least what should the correct exponent on the k be here? Okay, now we can also look at aperiodic infinite words. So this is just a word that is not eventually periodic, so it doesn't eventually start repeating itself. And these authors prove that if you have an aperiodic infinite word, then it has to contain a 3 antipower. And again, this just means that it has to contain a factor which can be broken up into 3 blocks of the same length so that those blocks are all distinct. However, this is not true if you replace the 3 with a 4. And there's a fairly simple construction for this. You can say, let's let alpha sub I, for I at least 1, be some sequence of positive integers that grows sufficiently fast. And by sufficiently fast, I just mean that alpha sub I plus 1 should always be at least 5 times alpha sub I. So just pick any sequence with this property, and then define x to be this basically this indicator function for this sequence. So it's just x1, x2, x3, and so on, where xn is defined to be 0 if n is not one of the terms in this alpha I sequence. And it's 1 if n is one of the terms in this sequence. So you can think of this as just like an infinite binary word where most of the letters are going to be zeros, but there are going to be a few ones sort of scattered kind of sparsely throughout. And the theorem is that this word x constructed here is aperiodic and it avoids 4 antipowers. It's not hard to see that it's aperiodic, and it's also not hard to see that it avoids 4 antipowers just because you say, well, imagine you take some factor that you can break up into 4 blocks of the same length, and then you just check that 2 of those blocks have to actually be the all zeros block because, again, the ones are kind of sparse in this word. Okay. Now, an infinite word is called uniformly recurrent if every finite factor that appears in the word actually appears infinitely often and with bounded gaps between the occurrences. And so maybe I should specify that this means once you fix the factor, then the bound between the gaps between the consecutive occurrences of that factor have to be bounded, but the bound could depend on which factor you choose. And the theorem here is that every aperiodic uniformly recurrent word must contain antipowers of all orders starting at every position. So one thing I'll mention here is that we're not saying anything about the lengths of the blocks in these antipowers, or equivalently the length of the antipower. We're just saying there is some, for any value of k, there is some k antipower starting at whatever position. But, you know, a priori, these k antipowers could be very long. And so later we're going to be talking about what are the actual sizes of the blocks. Can you guarantee that you can find antipowers where the blocks are actually somewhat small? That's sort of one thing that we can look at here. And also later I'll look at what happens if we drop the uniform in this and just talk about recurrent words instead of uniformly recurrent. And there something different happens. Okay, so one nice example of an aperiodic uniformly recurrent word is the 2A Morse word, which again, I probably don't have to define, but I will anyway. This is the word T, which is constructed by starting with a 0, and then at each step, we're going to take the complement of the word that we have, by which I mean just change all the zeros to ones and change all the ones to zeros. And then you append that to the end of the word that you already have. So here we have a 0, the complement of this is 1, so we append a 1 to the end and we get 0, 1. Now the complement of 0, 1 is 1, 0. So we'll append that to the end and we get 0, 1, 1, 0. The complement of this is going to be 1, 0, 0, 1. So we append that to the end, we get 0, 1, 1, 0, 1, 0, 0, 1. And if we keep going, we construct this infinite binary word called the 2A Morse word. And this is an aperiodic uniformly recurrent word. So that means that it has antipowers of all orders starting at every position. And so again, we can look at what are the actual sizes of these antipowers? In other words, what are the block lengths? So I'm going to define gamma of k to be the smallest positive integer m, such that the prefix, here I'm starting at the first position of the 2A Morse word, the prefix of the 2A Morse word of length km is a k antipower. So again, what this is saying is if you want to find out, if m works, you look at the first k blocks of length m in the 2A Morse word, and you ask if they're all distinct. And the smallest m for which that's the case is this gamma. So as an example, let's compute gamma of 3. So if we want to compute gamma of 3, we look at the first 3 blocks of length. Well, let's start with m equals 1. So the first 3 blocks of length 1 are just the first 3 letters, which are 0 and 1 and 1. Those are not all distinct because the 1 appears twice. So m equals 1 does not work here. So then if we look at m equals 2, we're going to look at the first 3 blocks of length 2, which are 0, 1, and 1, 0, and 1, 0. Those are not all distinct because the 1, 0 appears twice. So now we go to m equals 3. For m equals 3, we look at 0, 1, 1, and 0, 1, 0, and 0, 1, 1. Those are not all distinct because the 0, 1, 1 appears twice. If we go to m equals 4, we get 0, 1, 1, 0, and 1, 0, 0, 1, and 1, 0, 0, 1, which are not all distinct because of the 1, 0, 0, 1. And then finally, m equals 5 does work. So if we look at the first 3 blocks of length 5, they are 0, 1, 1, 0, 1, and 0, 0, 1, 1, 0, and 0, 1, 0, 1, 1. And those are all distinct. So gamma of 3 is 5. And so one thing you can ask is, well, what is the growth of this function gamma? How fast does this grow as a function of k? And these authors speculated that it should grow linearly with k. So this is something that I proved actually when I was an undergraduate at this Duluth math REU program. So this, I guess, was in the summer of 2016, although I put 2017 because that's when it was published. And I proved that the lim inf of gamma of k over k is somewhere between 1/4 and 9/10, and the lim sup is somewhere between 1/2 and 3/2. So the point is they're bounded by positive constants. And so again, I did this when I was an undergrad at this REU program, and then that same summer after I had written the paper, there was another student in the program. This was Shyam Narayanan. And he got interested in this topic and said that he wanted to work on this and try to improve my bounds. So he was able to use different methods to improve the lower bounds that I got. So Shyam showed, so again, I guess he did this in 2016, but it was published in 2018. He showed that the lim inf here is between 3/4 and 9/10, and that the lim sup is actually equal to 3/2. So notice that these are the same upper bounds that I had, but the lower bounds are now improved from 1/4 to 3/4 here, and then from 1/2 to 3/2 here, which matches the upper bound in the lim sup case. So I think it would be interesting to understand what this lim inf is, because we still don't have better bounds than this. I've conjectured that the truth should actually be 9/10, which I think is kind of interesting. It's not maybe the first number that I would have guessed, but this is what it appears to be just empirically. So even improving the lower bound beyond the 3/4, I think would be interesting to do. Okay, so I actually returned after being a student at this Duluth REU program in 2016, I returned as an advisor for the program in 2017, and I've also been an advisor every year since, and I'll be back there this summer for a few weeks. And in 2018, so this was like my second year of being an advisor, I gave this topic to one of the students, and this was Marissa Gates. And I suggested she look at the same kinds of questions, but starting at an arbitrary position in the 2A Morse word instead of just the first position. And so there was another student in the program who decided to call a factor starting at position J a jfix, because it's like a prefix, but it starts at position J. I don't know if this is like the right terminology, but I thought it was fine. So I'm sort of sticking with it for now. So we're looking at anti-power jfixes in the 2A Morse word. And instead of just looking at the minimum block length of an anti-power, we can look at just the set of block lengths of these anti-powers. So we're going to write AP sub j of tk to be the set of positive integers m such that the factor of length km in the 2A Morse word starting at position j is a k anti-power. Okay, so there's kind of a lot going on here, but there are really only two parameters that are kind of relevant here. One is the j, one is the k. And we're just saying you look at the 2A Morse word, you start at position j, you take the first k blocks of length m starting at that position, and if they're all distinct, then m is in this set, and if they're not all distinct, then m is not in this set. And we'll define gamma sub j of k to be the minimum element of this set. So when j equals 1, this is exactly what I was dealing with before with the gamma of k when I was talking about prefixes. So what Marissa proved is that for any value of j, the lim inf of gamma j of k over k is somewhere between 1/10 and 9/10, and the lim sup is somewhere between 1/5 and 3/2. So notice that these are the same upper bounds that I obtained, but the lower bounds are weaker. And I think this is indicative of the fact that there's something different about starting at an arbitrary position in the 2A Morse word rather than at a prefix. There are kind of nice properties of the prefixes that just fall apart when you go to arbitrary starting positions. And so basically this is saying that you couldn't just extend my methods immediately. It's not like you just say, oh, well, everything that Colin did just works and, we just write it down. There was some difficulty that Marissa had to overcome in order to understand the lower bounds here. And she's conjectured that the actual values of the lim_inf and the lim_sup should be independent of j. So they should be 9/10 and 3/2, which are the values that, well, 9/10 is the value that I conjectured when j equals 1, and then 3/2 is the value that Sham proved in the case of j equals 1. Are there any questions up to here? If not, I will keep going. Okay, so we can try to understand more about this set, a piece of j of tk. Again, this is like the set of block lengths of the k antipowers starting at position j. So it's not too hard to show, just using proper sort of the definition of the 2A Morse word, that if you have a positive integer m in this set, well, that will be the case if and only if 2m is in this set, in the case when j equals 1. So here I'm looking at prefixes, and I'm saying that if you look at the first k blocks of length m in the 2A Morse word, then they will all be distinct, if and only if the first k blocks of length 2m are all distinct. And so this means that if you want to understand this set, it really just suffices to understand the odd elements of this set. Now, this is not true if you replace the 1 by some other j. And this is sort of one of the difficulties that comes from moving from prefixes to other starting positions. You sort of lose this nice property here. But one of the nice things that Marissa proved is that if you fix some positive integer j, and you fix k at least 3, then this equivalence here, that m is in this set a piece of j of tk if and only if 2m is in the set, this will happen for all sufficiently large values of m. So once you fix j and k, this is basically saying that still it's enough to understand the odd elements of this set a piece of j of tk if you only care about sufficiently large values of m. Or I guess another way of saying this is that if you only focus on the odd values of m, then you're going to understand most of this set. You're going to lose a little information for small values, but you'll get most of the information. So still, it kind of makes sense to focus on the odd numbers in this set, even when j is not 1. Okay. So, okay, here's just a lemma about the 2A Morse word that I'll state, and then I'll go back to this a piece of j of tk. So this is a lemma that I proved in the paper that I wrote back in 2016 at this REU program. And I think I just prove it sort of by induction using the definition of the 2A Morse word. I think it's not trivial, but it's not like terribly difficult. It just says if you have some factor y, v, y in the 2A Morse word, so here y and v are just some words, and if the length of y is m, then this power of 2 has to divide the length of yv. Okay, so this you can think of as the smallest power of 2 that's greater than or equal to m over 3. And I'll just mention that this is tight in the sense that you could not replace this by the next power of 2. You couldn't replace this exponent by this plus 1. I'm not going to need that, but just this is sort of the optimal thing that you can say. Okay, so now using this, we can understand what I'll call capital gamma sub j of k, which will be the supremum of the set of odd positive integers that are not in the set a piece of j of tk. So again, this is the set of odd positive integers such that if you look at the factor of length km starting at position j in the 2A Morse word, then it is not a k antipower, meaning 2 of the blocks of length m have to be the same. And you might think, well, a priori, maybe this is infinite. And I think it is infinite for very small values of k, like k equals 1 or 2. But if k is at least 3, it turns out that this is finite. And we can show that it's actually at most 3k. And so the way we can do this, I'll just sketch the proof here. It's not too hard once we have this lemma. So we say, suppose we have some positive integer m. So it's an odd positive integer that is not in a piece of j of tk. And I want to show that m is at most 3k. So what does it mean to be not in the set a piece of j of tk? It means that, well, I can I can take the k blocks of length m starting at position j, and I can index them as like the 0th block, and then the first block, the second block, all the way up to the k minus first block. And this is just saying that I can find indices in 1 and in 2 so that the blocks with those indices are the same. And more precisely, these blocks are what I've written here. This is, so my notation, I guess, is that t sub I is the ith letter in the 2A Morse word. And so this would be this block starting at position in 1 m plus j and going to position in 1 plus 1 m plus j minus 1. And then similarly, this is the block starting at position in 2 m plus j. And the hypothesis here is that these are the same. And I'll call this word y. And then v is just going to be the stuff between these two factors in the 2A Morse word. So we have this occurrence of y, and then following that will be v, and then following that again will be this other occurrence of y. So we're in exactly this setting of the lemma where we have this factor yvy in the 2A Morse word, and the length of y is m. So that means that we can apply this lemma to say that this power of 2 has to divide the length of yv. So the length of y is m. Okay, so the lemma says that this power of 2 divides the length of yv, which is n2 minus n1 times m. But now the key here, which is why this is useful, is that m is odd. And that means that if this power of 2 is dividing this number and m is odd, well then the power of 2 actually has to divide n2 minus n1. And then that means that, well, okay, k minus 1 is at least n2, n2 is at least n2 minus n1, and then n2 minus n1 has to be at least this power of 2 because it's divisible by that power of 2 and it's a positive number. So this is some way that we can get a lower bound on this gap between n1 and n2. And then that tells us, if we just say, okay, this power of 2 is roughly m over 3. It's a little bit bigger than m over 3. And so if that's less than or equal to k minus 1, this is saying that m is at most 3k. Okay, so that's what we wanted to prove. And I'll just mention that this kind of trick here where we're using this divisibility condition, we're saying, okay, you can show that some power of 2 divides so the length of some factor, but then this part here is odd, so you can get rid of that. This trick is something that I also use later with Aaron Berger. We wrote another paper about antipowers in aperiodic recurrent words, and I'll mention that later. Okay. So again, we can look at this capital gamma sub j of k. Here I'm taking j equals 1. Remember, this is the supremum, or really we could say maximum if k is at least 3, since we know it's finite. It's the maximum odd positive integer that's not in the set AP sub j of tk. And the lim inf turns out is 3/2, and the lim sup is 3. And then Marissa was able to extend this to other values of j as well. So again, the lim inf is 3/2, and the lim sup is 3. So maybe one thing I'll mention is that so far we've kind of looked at the extreme parts of this set AP sub j of tk. We've talked about the minimum element. This was the little gamma sub j of k. And we've talked about the maximum the maximum odd number that's not in the set. But we haven't really said anything about what's going on between those values. Like what is, in other words, how big is this set? How sparsely distributed are the elements of this set? So I think this is maybe an interesting question to explore. I haven't really looked into this, and as far as I'm aware, no one else has. But basically, this would be just saying like, okay, we have this kind of range where it's interesting to look at this set going from, well, basically going up to this capital gamma sub j of k, which is the maximum value of this set. And we have estimates for what that maximum actually is. You can say, well, going up there, are there very few elements of this set, or are there a lot of them? And of course, another thing you could do here is just replace the 2A Morse word with some other interesting word. Everything here has been for the 2A Morse word, but you could really look at like lots of other words. I think this again is pretty unexplored. You could look at like the Fibonacci word or other, I don't know, other interesting words that people like. And all these same questions about the little gamma sub j of k, you can look at the set AP sub j of k and the capital gamma and all this stuff you could define and study. Okay, so now I want to go back to this aperiodic recurrent word stuff. So remember, I said that a word is is uniformly recurrent if every finite factor that appears in the word appears infinitely often with bounded gaps between the occurrences of the factor. Here, I'm going to remove this bounded gaps hypothesis and just say that it's recurrent if every finite factor that appears actually appears infinitely often, but we don't require bounded gaps. So again, I said this before, but these authors prove that every aperiodic word has to contain a 3 antipower. But it turns out that you can have aperiodic recurrent words that do not contain 6 antipowers. Okay, so remember, if you have an aperiodic uniformly recurrent word, it must contain k antipowers for all values of k. So what this is saying is that if you change uniformly recurrent to just recurrent, then that goes away, and now you can actually find words that are recurrent, but not uniformly recurrent, that avoid 6 antipowers. And the construction of this is pretty simple. Well, I guess maybe once you have the idea to do this construction, then the construction is simple. I don't know how difficult it was to come up with this. But they said, okay, take W0 equals 0. And then for n at least 1, just recursively define Wn to be Wn minus 1, concatenated with a bunch of copies of the letter 1. So we're taking 3 times the size of W sub n minus 1 copies of 1. And then we add on another copy of Wn minus 1. So this is going to be some recurrence that gives us these longer and longer words. And in the limit, we get this word W. And then the fact here is that this word is aperiodic. That's easy to check. But then also it's recurrent. That's also easy to check. And it avoids 6 antipowers. And that they have to go through an argument to show that it avoids 6 antipowers, but it's not too long, I guess. Okay, so if you combine these two theorems, then it's natural to ask, what is the largest positive integer k, such that every aperiodic recurrent word must contain a k antipower? So these two theorems are saying that it has to be either 3 or 4 or 5. And it turns out that the answer is 5. And so this is something that Aaron Berger and I proved. So maybe I can relate this also back to the Duluth REU. So Aaron was actually a student in 2016, the same year that I was a student. But then later, I think we were at the joint math meetings, and he came up to me and said, hey, we should work on this open problem that was in this paper about this largest value of k. And I said, okay. And so then we started working on it and wrote this paper. Okay, so yeah, basically this is saying that this bound here, or that this 6 here is tight. You can't improve the 6 to a 5. Okay. So now I want to shift to looking at aperiodic words that are fixed by morphisms. So I'll just remind you of what the definition here is. I'm going to let a to the less than or equal to omega be the set of words over some alphabet a. And a morphism is just, so maybe I should say by this set of words, I mean finite words, but also infinite words that are infinite in one direction. So like maybe infinite to the right. And a morphism is just a map mu from the set of words to itself that factors through concatenation. So mu of uv is mu of u, mu of v for all words u and v. And if you have a morphism, then it's uniquely determined by specifying what it does to the letters in the alphabet, because if you just take any word, then you can factor it into its letters and then just apply the morphism to each of the letters independently. And then a morphism is called R uniform if each letter in the alphabet gets sent to a word of length R. So a nice example of this is the to-a Morse word. We can look at this morphism mu, which sends the letter 0 to 0, 1, and it sends the letter 1 to 1, 0. And this is a 2 uniform morphism because each letter gets sent to a word of length 2. And the 2a Morse word is a fixed point of this morphism, just meaning that if you apply this morphism to each letter in the 2a Morse word, you will get back the 2a Morse word. And so these words that are fixed by morphisms are really nice, and they have a lot of interesting properties. And so we have this conjecture. I've put conjecture in quotes because it's not super precise, but I'll say what I mean by this in a minute. So the conjecture is that if we have some word W, which is sufficiently well behaved, I'll say what I mean by that, and it's aperiodic, and let's assume that it's fixed by some morphism mu, then there should be some constant C, only depending on the word, such that for all positive integers j and k, this word will contain a k antipower starting at position j in the word, with blocks of length at most c times k. So here again, we're looking at the lengths of the blocks in the antipowers. Another way of saying this is, instead of saying that the blocks have length at most ck, since there are k of these blocks, this is equivalent to saying that the antipower itself, as a word, has length at most c times k squared. Okay, and basically what I mean by sufficiently well behaved is just that, well, maybe a better way of saying this would be to pose this as a problem, although I guess in the paper we made it a conjecture, but I guess it would be an open problem where the problem is to characterize the words where this is not true. And the sort of conjecture is that it should be basically most words with these properties, except there might be a few exceptions where you can just write it down explicitly. So, and maybe just sort of for obvious reasons. There might be sort of obvious words that you can write down where you say, okay, well, obviously it doesn't work for these words, but for most other words, this will be true. Now, I should say for the 2a Morse word, this is essentially what Marissa was doing in Duluth back in 2018. Because remember, she was looking at the lengths of the antipower j fixes in the 2a Morse word. So it essentially follows from what she was doing that this conjecture is true for the 2a Morse word. And so one of the things that, so this is just the conjecture written again. One of the things that Aaron and I did in our paper is we proved that this conjecture is true for binary words that are fixed by uniform morphisms. So we're assuming that the alphabet has size 2, and we're also assuming that the morphism is R uniform for some value of R. And this is the theorem where we kind of use this divisibility trick from before. Because the word is, or because the morphism is R uniform, you can prove an analog of that lemma that I had for the 2a Morse word. But instead of saying that some power of 2 divides the length of some factor, you end up getting some power of R dividing the length of the factor. And then you do the same kind of trick where you say, okay, basically this power of R has to divide some product of 2 numbers, but one of the numbers in the product is relatively prime to R, so you can get rid of it, and then you get this extra information about the size, like a lower bound on the size of this extra quantity, and that allows you to prove something like this. So Swapnil Garg was actually a student in Duluth in 2019, and he proved that this conjecture is true for words that are fixed by uniform morphisms, but without the binary hypothesis. And then independently, using different methods, Postic proved the same result. So we now know sort of doubly that this is true for words that are fixed by uniform morphisms. But we still haven't, it's still open to try to remove this uniform condition. And the first progress that was kind of made toward removing the uniform hypothesis here was also done by Garg in the same paper. And he showed that this is true for the Fibonacci word. So the Fibonacci word is this word that's fixed by this morphism mu of 0 equals 0, 1, and mu of 1 equals 0. So notice that it's not uniform because 0 gets sent to a word of length 2, whereas 1 gets sent to a word of length 1. But he proved that this conjecture still works for the Fibonacci word. And explicitly, he showed that for all j and k, this Fibonacci word must contain a k antipower starting at position j with blocks of length at most 2.89 times k. So this constant capital C that we had from before, in this case, could be taken to be 2.89. I don't think he tried to optimize this. So this is not claiming that this is like the optimal constant. Maybe you can do better than that. Maybe that would be interesting to see, how far down can you push this for the Fibonacci word. Also, again, there are other interesting words beyond the two Morse word and the Fibonacci word where you can try to say, okay, not only do we know that this constant exists, but maybe we can try to find estimates for it and see what's going on there. So yeah. All right, so I think that is all that I had to say. Maybe one thing I will mention before I finish is just, I don't think I mentioned anything here about abelian antipowers, but this is something that I realized people have worked on a little bit. And an abelian antipower is basically where you say, okay, break it up into these k blocks of the same length. And instead of requiring all the blocks to be distinct, you require them to be distinct modulo reordering the words. So in other words, you can associate to any word just some vector that keeps track of how many occurrences of each letter there are in this word. And then you want to look at all of these k blocks and say that those vectors associated to the blocks are actually distinct. Okay, but I don't have anything prepared to say specifically about the abelian antipowers. I haven't looked into them too much, except I've just seen that people have done stuff with them. But anyway, that's all. So thank you.
Thanks, Colin. Does anyone have any questions for Colin? So I was wondering, do you sort of recall what the rough idea of what the Garg's techniques were for Fibonacci?
No, not really. Yeah, unfortunately, I don't. Yeah.
Okay, yeah, I was just sort of curious if, well, if it was sort of some kind of, it's probably not some kind of divisibility trick, like.
Right, I think it's not the divisibility, and I mean, it does use specific properties of the Fibonacci word, so I don't think it generalizes immediately to, more general words. Maybe there's a way of generalizing it a little, but.
Or maybe the Sturmian words, maybe,
Yeah.
maybe his methods might work for general Sturmian words.
Right.
It's some kind of frequency thing, or. Yeah, Alessandro, did you have a question?
Yeah. Hi. Does the result on fixed point of uniform morphism extend to automatic words, so codings of those fixed points?
Oh, I think we looked into this, but we didn't see an immediate way to extend it. It could be that we didn't try hard enough, but I think we did think about this and we thought, okay, we don't really know how to do this. Although I guess now there are these other papers, by Garg and Postic, maybe their methods would extend, but I think at least the methods that Aaron Berger and I used, we thought didn't really do much for the codings of these words.
Okay, thanks.
Are there any other questions?